Here we're going to start talking about voltage divider circuits. And in the subsequent sections we'll talk about current divider circuits. So these topics go a little bit hand in hand. They're very similar to one another. But here we're going to focus on what we call the voltage divider. It's a very simple kind of circuit that has a very specific purpose, and it's very descriptive. It says we're going to divide the voltage. We're going to divide the voltage up, right? So what that means is, let's say I have a power supply that is plugged into the wall and it's feeding my circuit with a, let's say I convert it to DC, so it's a DC guy, or let's say I have a battery, a 12-volt battery or something like that. But let's say that that battery I have is the only battery I have and it's 12 volts. But let's say my circuit doesn't operate at 12 volts. Let's say my circuit is like a computer. Lots of computer chips, especially older ones, operate at 5 volts. And a lot of them operate at lower voltages now, but let's say that your circuit, for whatever reason, only operates at 5 volts. That's all it needs, that's all it wants. If you give it more than that, you'll burn the thing up, right? So you would like to somehow use this battery that's 12 volts to supply your circuit that only needs 5 volts. So you really want to figure out a way to do that. Now there's many ways to do that, but one way to do it is to design a voltage divider. Some combination of resistors that I'll show you that we can do that will split that voltage up, that 12 volts up, so that I can tap off 5 volts of it, let's say, and then use that for some purpose, some load, which is our circuit that we're trying to do. So when we talk about loads, you know, we're talking about the function we're doing, the circuit that's operating. When we connect the load, we're connecting whatever it is we're using, whatever it is we're powering. All right, so that's the big picture of what we're trying to do. Let me show you how you might pull that off. Let's say in this case, instead of 12 volts, let's make it a little bit easier. Let's say we have 10 volts. And let's say I connect this guy like this. Believe it or not, this is a voltage divider circuit. We just never really told you that. So, you know, get it out of your head that it's difficult. It's stuff that we've been learning all the time. I just never really told you it's a voltage divider. And let's say we have 5 ohms for this resistor and 5 ohms for this resistor. Take note, these two resistors are the same value. They are the same. All right, now let me show you what's actually happening here. Let me show you what's actually happening here. So what we have here is there's some current I flowing, obviously, and it's flowing through both of these guys. Let me switch colors. And you know from our example so far that when the current flows through this resistor, there will be a voltage drop. And then when it goes through the following resistor, it will be another voltage drop. So this voltage drop, looks plus to minus, and it has a voltage drop V, and then this resistor has a voltage drop V. And you know from Kirchhoff's laws before that this voltage drop plus this voltage drop must equal the 10 volts. Because if you do a Kirchhoff loop here, this is a simple circuit, you could do a loop, right? The 10 volts here minus this, or I should say the way it would work is if you did a loop, it would be whatever voltage is here plus whatever voltage is here has got to, minus this voltage up here because this is negative, has got to be equal to 0. So the sum of these voltages have to add up to the 10 volts. I mean, when you look at it, the thing is physically connected to the source. So the 10 volts is across the whole thing. So the voltage here and the voltage here, V1 and V2, if you want to call it that, they must sum up to 10 volts. Now, how do they do that? Well, the punchline is, because I've chosen the same value, the actual value of 5 ohms doesn't really matter. What's more important is that I've chosen the same value here as I have for here. And because I have done that, this is very important, because I have done that, the voltage across this top thing is going to be 5 volts, and the voltage across this bottom resistor is also going to be 5 volts. So really what I've done is I've taken my source voltage and I have split it up by allowing this voltage drop to occur across 2 different resistors. They happen to be the same value, and because they are the same value, I have the same voltage across both of them. And because they have to sum up to 10, this happens to be 5 and this happens to be 5. So I'm going to get into the math to show you why this is the case in a minute, but just suffice it to say that it all depends on the ratio of these resistors. If I choose a very specific ratio of equal amounts, then I'm going to split the voltage equally. If I put a very small resistor up here and a very big resistor down here, then a tiny amount of the voltage drop is going to be across this one, and a very large amount of the voltage drop is going to be across the one that's in series with it. So when you design a voltage divider, you're going to be jockeying the values of these resistors to give you whatever output voltage you want. So in this case, maybe I want 10, or maybe I want 5 volts. Maybe I want to connect 5 volts to some other circuit. So I would literally have a circuit I designed out here, and I would connect the leads here, right across this resistor. And that's going to supply current at, and I'll talk a little bit about this, in a perfect world, 5 volts directly to my load, right? Now let me show you briefly why this is the case. And I've kind of already really done it, but I want to make sure you understand it. This circuit has 5 ohms and 5 ohms. So if we add them together, we get 10 ohms. 10 ohms equivalent resistance. So if I want to find the current here, the current is V over R. The voltage is 10 volts. The equivalent resistance, when you add them together, is also 10 volts. So the current is 1 amp flowing through here. The current is 1 amp flowing through there. So that means that the voltage across here, you can see now why. V is equal to IR. 1 amp, 5 ohms, 5 volts. And exactly the same thing happens here. 1 amp, 5 ohms, 5 volts. Right? So it's all self-consistent with Ohm's law. You see, I'm not inventing something else saying, oh, this is a special voltage divider. You just have to memorize it. It's not like that in circuits. Everything makes sense from the core values of Kirchhoff's laws and Ohm's law and the fundamental things we've learned. So there's nothing really new here. It's just an application of what we already know and some intuition that comes as a result. So this is the bottom line. I can, if I want 5 volts, or I should say in this particular case, if I want to divide this source in two, I would choose 2 equal resistors. Now let me show you another example of how it might be different. Let's say I have, again, 10 volts just to make it easy, and I have 2 resistors again here just to make it easy. But instead of it being split up this way, let's say I have 8 ohms and I have 2 ohms. Then what's going to happen here? Well, you know, a similar thing is going to happen. There's going to be a voltage drop across this resistor. There's going to be another voltage drop across this resistor. You need to start getting the intuition to know that since this 10 volts is connected across both of them, they both have to add to 10 volts. We kind of learned that from Kirchhoff's laws, but you need to internalize that. The voltage drop across both of these must equal the source voltage, right? And also, because this one's larger, it's going to get the majority of the voltage drop. This one's smaller, so it's going to get less of a voltage drop, and it's always in relation to the ratio of these resistors. The bigger one's going to get more of the voltage drop. The smaller one is going to get less of a voltage drop. So in this particular case, if you want to work out the math, the current here, right, we have a current flowing. The current is V over R. V over R. The voltage is 10. What's the equivalent resistance? I've chosen this carefully so it still is 10 ohms. Because you add them together. So again, it's 1 amp, right? So the voltage across the 8 ohm resistor is IR, which is 1 amp times 8 ohms, which is 8 volts. And the voltage across the 2 ohm resistor is IR, and it's 1 amp flowing through it, times 2 ohms is 2 volts. So what I've really done here is I've proven to you that the voltage drop, if I were to draw it here, right, like this, this voltage drop is 8 volts. And this voltage drop is 2 volts. But they have to sum to 10 volts, and that's the way it always is. So it doesn't matter the value of these resistors you choose, it only matters how they're sort of proportional, how the ratio between them. The bigger one, if I made this one 100 million ohms and this one 1 ohm, then this voltage would be the 99.9% of the entire voltage, and this guy down here would just get a teeny smidgen of voltage drop because of Ohm's law and the way it really all works out. All right, so again, maybe my circuit that I'm building in this particular case, maybe I only want 2 volts. Maybe it only operates at 2 volts, right? So if that's true, then I would connect something here, I would connect something here, and I would hook up what I'm calling my load. This could be a light bulb. This could be some computer chip. It could be anything I want. But if I only have a 10 volt source available, but I really need 2 volts to accommodate my load, then I'm going to end up hooking it up like this. Now I need to specify something that's very, very important. When I do not connect the load here, before I connect the load, right? So I made a little bit of a mess here, but you can see there's nothing connected there. There's a pure and perfect 2 volts across this source, right? 2 volts across this resistor. It's governed by all the Ohm's laws that we've talked about, right? Now when you think about it, as soon as I connect the load, which is some resistors, right? Like if it's a light bulb, it's a resistor. That's what a light bulb is. So let's just pretend it's a light bulb for the sake of discussion, right? So I hook a light bulb up to this. At the moment I hook a load up to it, then I've altered the circuit, right? It's no longer pure the way I originally designed it. If I hook a light bulb up to it, I'm introducing another resistance here. And if I put another resistance here, the resistance of the load, right? Then this resistance is in parallel with my 2 ohms. So if I screw up and put the wrong kind of resistance here, I can change the value of this whole area of the circuit, which will alter the voltage going into my load. Let me say that one more time. A lot of times in circuits, when you're talking about voltage dividers, they'll ask you, calculate the no-load voltage, the no-load voltage. When they say that, they mean they want you to calculate the voltage across the terminals that we're interested in, but with no load connected there. That's perfect. That's a perfect 2 volts delivered there, right? Now, if I connect a load, depending on the resistance value of my load, I'm going to actually change the circuit, and I'm not going to have really 2 volts delivered right across that guy again, because I'm really changing the resistor network. Now, let me ask you this. How can I minimize this guy, right? Look at the way I've got it drawn here. I've got nothing here. I've got basically infinity resistance, right? So I kind of help you out here. Infinity resistance, right? In other words, it's open circuit here. So if I connect a load that has a very, very high resistance to my voltage divider, then I haven't really altered anything. I haven't really altered my circuit. So I'm still having a pure 2 volts delivered. Everything is cool, right? But if I hook up a load with a small resistance, right, like maybe a 10 ohms or something like that, something comparable to what I have here, then these are in parallel. It changes the equivalent resistance, which is going to change how the voltages are distributed, which is going to change the voltage that I'm getting in my load, which means if my load requires 2 volts, and if I hook up a fairly low resistance to it, then suddenly I don't get 2 volts into my load. I get something less than that because I've altered it, right? So you've all heard of a voltmeter, right? You've heard of how you measure circuits, right? Or maybe you've seen it, right? So you have a circuit here, you want to measure the voltage. You have 2 probes here, right? And you're literally jabbing them into the circuit. So how do they design that thing? How does that not alter the circuit? When you think about it, you've got resistors. If you hook up a voltmeter, shouldn't it alter the circuit? Shouldn't it change what you're measuring because you're hooking something else into the circuit? That's true, but when they design these voltmeters, they make sure, and here's the punchline, that they have extremely high internal resistance. And the way that they do that is not relevant. The way that they pull it off is beyond the scope of what I'm talking about. But when they build voltmeters, they make sure that the internal resistance of that meter is extremely high. So that if I hook my terminals across this resistor to measure its voltage, I have basically infinity resistance, infinite resistance. So it's almost like not having anything there at all. Super high resistance means no current is going to flow into this leg. It's all going to continue to go through the 2 ohm resistor. It's not going to alter much. It's going to alter teeny tiny bit, but if I make it a high enough resistance, it's not going to be a big deal. So that's how we design voltmeters. All right, so to recap before we do a problem, here's a voltage divider. I'm going to show you how to calculate easily how the voltages are divided in a second here. If you don't have any load connected at all, it's called the no load voltage on my output terminals. Once I connect something to it, it's called the loaded down voltage. And depending on the resistance of whatever it is I hook up, I may change things a little bit and maybe I won't get exactly 2 volts out. It depends on the resistance. The higher the resistor value of whatever it is I connect here, the more pure my original voltage divider is, and the exact amount of voltage drop that I calculate is what I'm going to actually get. The lower and lower and lower voltage, if you think about it, if you drive this resistance to a short circuit, what's going to happen? Now it's a short circuit. Zero resistance. What's going to happen here? Well, all the current, none of the current's going to go through this resistor. All the current's going to go zoom, right around. I've completely altered it. I'm going to get 0 volts over here because I've got no current through this resistor, and there's always 0 volts when you have a wire there. There's no voltage drop across a pure wire. So in the limiting cases, super high resistance connected, perfect, don't alter the circuit very much. You're getting what you calculated as far as your no load voltage. Other end of the spectrum, you connect 0 volts, short circuit, you get no voltage across your output leads and no usable, you've got no usable voltage in your load, basically. All right, so now we need to stop talking about it a little bit and jump to the punchline a little bit. And let me show you what the what the voltage divider guy is. So let me quickly draw. Here is we have some input voltage V, right? And we have two resistors. We're always going to be constructing our voltage dividers out of resistors. Okay, and then we have here R sub 1 and R sub 2. And what we're interested in doing, let's say, is tapping off a voltage right here. And we're going to call that V sub naught. And this is what's going to end up being connected to some load. Now, we don't know what this is. We don't know what this is. We don't know what this is. We're showing you an equation to really do that. The bottom line, when you use Ohm's law and figure it all out, and I've kind of alluded to that a little bit before, is the following. V naught, which is the output voltage you care about going to your load, is equal to the input voltage, right? Got to have something you start with, so I'll put Vs here, make it V source, times, since it's tapped off of R2, R2 divided by R1 plus R2. And this is a voltage divider. I'm going to put no load. All right? All right, so what this means is if I build a circuit like this and hook a voltmeter across and measure, remember voltmeter has super high resistance so we don't alter the circuit. What you're doing here, see, you look at these equations and a lot of times students are like, okay, great, I'll memorize that. But don't do that. Try to understand what it's telling you. What it's saying is, when you cover up this for a second, what you've got here is it's kind of like a ratio. It's like, how does R2 compare to the sum of both of these resistors? In other words, if R2 is very, very big, right, if it's the largest guy, then this numerator is going to dominate, and the denominator, since it's R1 plus R2, is going to be just a little bit bigger. So this, in other words, this fraction is always going to be a number less than 1. That's sort of the bottom line. But if R2 is very large, it's going to be a number very close to 1. Because if this is 1 million, and then this is 1 million, and this is like 1 ohm, then it's going to be 1 million divided by 1 million and 1. So you're going to get a very high, you're going to get 0.999 something, right? And then you're going to multiply by the 10 volts you started with, or whatever it is, very large number close to 1, times your source voltage. It means that almost all of your voltage drop is going to be across this resistor. That's what I told you before. If this guy's very high, most of your voltage drop is going to be across him. If this guy's very low compared to the other resistor, very little of the voltage is going to be across him. If this guy's very small, very close to 1, let's say this is 1 ohm and R1 is 100 ohms or something, then I'm going to have 1 divided by, I'm going to have 100 ohms here plus 1, so 101. So 1 divided by 101. I'm getting a very small number times my source voltage, which means I'm going to get almost nothing there. So this is in math telling you what I've already said. If this is small compared to this guy, you're not going to get much voltage out. If this is large compared to this guy, you're going to get the majority of the voltage across. But don't forget, this is all assuming no load. This is assuming nothing is connected to the end. As soon as you connect something, you have to reevaluate everything to make sure, because it might change things a little bit as far as the resistance. So what I'm going to do now is erase this. Let's work a problem. And I think your understanding of this will go through the roof once we actually can do a real problem. So let's go ahead and do that. It's a very simple problem to kind of write down. So I have 120 volts. And so here I have a resistor like this, connected like this. This one is 30 kilo ohms, right? This one's 50 kilo ohms. And let me kind of draw out here. I'm connecting off the bottom resistor. Now I have another resistor here, RL, that means a load resistor. And we can draw little some terminals here if you want. What this basically means is I can detach the load or I can hook up the load or whatever. And so there's some voltage, you know, that I'm tapping off, V naught. That's what I want to know. So there's two questions here. What is the no load V naught? What is the no load output voltage? And then the second part is, what if I hook up 450 kilo ohms as a load? So let's do the first part first. So let's just say no load V naught. I'll put a question mark here. So this is simple. What it means is you cover this up. There's no load there at all. You have a voltage divider. You want to know what's the voltage across the 50 kilo ohm resistor. You basically back up and use what we already just said. So V naught is equal to the source voltage times, in this case, it's going to be R2 over R1 plus R2. I'm just kind of saying this is R1 and R2. We can think of it however you want. But what you have here, V sub S, that's 120 volts. The resistor in question is the one you're putting there. It's basically the resistor you're tapping off of divided by the sum of the two resistors. So here I have 50 kilo ohms. Don't put 50, put 50 times 10 to the 3, because that's kilo ohms. On the bottom, it's R1, 30 times 10 to the 3 plus 50 times 10 to the 3. Right? So what you need to do is add all these things together and do the division. So you add this, you divide. So what you're going to get is V naught is 120. Inside here it should always be a decimal. And what you're going to get when you take this and you divide by this, you're going to get 0.625. So V naught, when you multiply by 120, is 75 volts. And I'm going to put no load. Just like this. So this is what we call a no load voltage. All you do is you have the source voltage multiplied by something in there. It's the resistor value we're tapping off of divided by the sum of the two resistors. It's splitting the voltage up proportionally, and you can see that now. Because I'm doing this guy, I get a decimal. It's 0.625, so I'm getting a little bit over half of the voltage falling across this. That makes sense. 50 is bigger than 30 by just a little bit, so just a little bit more than half of the voltage should be across this resistor. All right, now here's the punchline for the problem. This is why I really want to do it. What is V naught when the resistor, load resistor, is 450 kilo ohms? What happens there? All right, so what we're saying is we hook up a value, we hook up a load. That load happens to have an internal resistance of 450 kilo ohms. What we want to figure out now is, now that we've hooked up a resistor, what is the output voltage across it, right? So there's lots of different ways you can do it, but the way I think you should do it is you notice right away, this resistor is in parallel with this. So let's do a parallel combination first. So what I'll write down is the parallel combo between the resistor, the load resistor, and the 50 kilo ohms. So the equivalent resistance is equal to, remember we talked about that in the last section, product over sum, product over sum, product over sum. So the product is going to be 50 times 10 to the 3 times 450 times 10 to the 3, that's multiplying both of them, divided by the sum. 50 times 10 to the 3 plus 450 times 10 to the 3. Lots of exponentials everywhere. It's kind of a little bit of a pain. But whenever you multiply these things together, divided by the sum of these things, you get something reasonable. 45,000 ohms, or 45 kilo ohms. Right? So notice what happened is, we hook the load up. And because we hooked the load up, when you now look at the circuit again, you don't see this. You see another resistor down here that's not 50, but it's actually 45. 45 kilo ohms. So let me kind of redraw. I don't have enough room there. Let me redraw the circuit here. So we have 120. Top resistor is 30 kilo ohms. The bottom resistor now sort of becomes, what did I say, 45 kilo ohms. The reason it looks like this now is because I've hooked up the load, right? It's because I've hooked up the load. We've altered the circuit. It's no longer the same. So the output voltage, which is again across this resistor, is not going to be exactly what we calculated in the first place, because now that bottom resistor, this resistor, is different. So to find the loaded down voltage, we need to do voltage divider again, tapping off from the same place, from here, from the 45 kilo ohm resistor. So now let's do that. Let's say the output voltage is equal to Vs times, let's do R2, R1 plus R2. Of course, it's multiplied together. So Vs is 120. All right, R2, that is our resistor we're tapping off of. It's now 45 kilo ohms, so we'll do 45 times 10 to the 3. And now we do a sum. So here we have 30 and 45. So we have 30 times 10 to the 3 plus 45 times 10 to the 3. We close that off. So we do this guy, we do the division there. What we're going to get here is 120 times 0.6. And then when we do that multiplication, we'll get 72. Let's just rewrite it here. V naught is 72 volts, and I'm going to put loaded, just to make sure everybody understands. Now look at the difference. What has happened is, if we don't hook any load up, we get 75 volts across here. So we might design our circuit and we might say, all right, I need 75 volts to hook up to my load. Great. I design a voltage divider, 75 volts, bammo. Then, if you poorly design your circuit, you hook up this guy, and then you measure it again, and you get 72, and you scratch your head, and you're like, how is that? I calculated it should be 75 volts. But I'm only getting 72 volts. That's not enough to run my pump or my fan or whatever it is I'm trying to do. What have I done wrong? What you've done wrong is you've completely ignored the fact that whenever you added your load, you have changed the voltage divider. That's what you've done, right? And so you can see that because this is still a very large resistor, 450,000 ohms is a very large resistor, even compared to this. So whenever you add this guy, it only dips by 3 volts, right? It only dips by 3 volts. I guarantee if you added a 50 kilo ohm resistor here, or even a 100 kilo ohm resistor, the lower the value of the resistance, you're going to get a much larger deviation in the voltage that's delivered to that load, right? Because you're altering the circuit more. If you go the other direction, like we said a minute ago, if you make this a million ohms, or 10 million ohms, or internal resistance of 25 million ohms, and you do all these calculations again, you're going to get something extremely close to 75 volts. So most voltmeters, when you hook them up to a circuit and measure, the internal resistance of those meters are very typically in the millions of ohms. Very, very high resistances, so as to not to alter, because ultimately you don't want any current flowing in that voltmeter. You just want a pure, voltage there. So there are other considerations, depending on what you're trying to do in your circuit, what the purpose of what you're trying to do is. But the point of this lesson is to tell you the no load voltage is what you calculate when you don't have anything connected there. You just do the voltage divider law. When you load it down, first you find a parallel combination of what you've hooked up, and then you do the voltage divider again. And the deviation from what you got the first time is going to be more apparent if you choose a low value of your load resistance. It'll be more in line with what you calculate with no load the closer and closer you get to infinity for R sub L. Because when you think about it, if R sub L really becomes infinity, it's like no load at all. So that kind of makes sense. So we are done with this section, introduced voltage dividers. And so we're going to go on into the next section and do a couple more problems to get you more comfortable with the idea of voltage dividers and how they apply in circuits. Learn anything at mathandscience.com.